Hello, my name's Colin Hendrie. I'm a senior lecturer in human and animal ethology in the Institute of Psychological Sciences, the University of Leeds. My interest is in human and animal behaviour, and particularly in evolution. And this is what this series of podcasts is about. This is the third in a series of 4, and this part is going to talk about what makes humans unique and what makes us special. From the slide, you can see one of the things that stands out immediately is that we walk and we locomote differently to the other species that are in our group. And you can see that the loris and the lemur are leaping around. You can see the baboons are walking on all 4s. You can see the brachiators on the go there. And then you see humans balanced on their hind legs in this very strange way that looks very odd in the context. When did all this start? Well, the picture there is of almost a snapshot of history. It shows a wonderful, very human-like behaviour. It's a pattern of footprints that are in ash that have been fossilised. It's very human-like because it shows an adult with a small child walking next to them, almost a family captured in the moment of time. The charts on the other side there show you where bipedalism actually started in our species. And in the very early species, what you start to see is the semblance of bipedalism, but think more like a chimpanzee walking on its back legs. It can do it, but it's very unstable. It's not something that it would prefer to do the whole time. And as our species then move through time, what happens is we get better and better at the bipedal locomotion, and eventually we become fully bipedal. Why did this happen? Well, we can discuss this in a moment, but what's the benefits of it happening? Well, it's a more efficient way to locomote. Once you get through that transition phase, it's actually energy saving compared to running along on all 3s like chimpanzees do, or all 4s like the baboons do. Here we're looking at some of the most famous human fossils that are there. We've got Lucy and we've got Takana Boy. They're bones, they're bits of bones. Some fossils or some of the skeletons are almost complete, but what we don't have ever almost is a complete skeleton from one individual. What we have is bits and pieces, and the picture of the species is made up from a collection of different fossils from usually different locations. So how can we say things like this species walked on its hind legs? How can we say this one was bipedal and this one wasn't? Well, it depends a lot on the morphological features of the skull. And earlier what we did was to look at this particular skull. There's a hole in the back, and that's the place where the spinal column goes into the skull, into the brain, and the location of that is actually quite important, because if it's in the wrong place as far as an upright species is concerned, if it's too far back, then the balance is wrong. What happens is that the head won't sit in the right place, so as the species became bipedal, that hole, the foramen magnum, moved forward, which meant that the skull could nicely balance now on top of the spinal column. So that movement is how we can tell, one of the reasons why we can tell whether a species was bipedal or not. The second reason is that the muscle attachments required in an upright species are different from the muscle attachments for those in a quadrupedal species. And here you see the same muscles, or the homologous muscles, in a chimpanzee and a human, and you can see that the shoulder muscles are extended. Most interestingly, we have the gluteus maximus, and so basically we have a bottom. And effectively what's that there for is to stop you swaying, to stop you falling around, and just simply disappearing onto the ground. So that muscles have moved, and we can see the shadows of those muscle attachments on the bones that we find in the fossil record. But bipedalism itself is good for locomotion, but it's bad for other things, and it's bad for probably the most important thing that a species has got to do, at least the female of the species, and that's to reproduce. As the species becomes upright, what happens is that the hips must become narrower. Okay, this is the way that stability is achieved. If the hips are too wide, then the mechanics of it are unstable. So what happens is that the hips become narrow, and they become narrow to the point where they can become stable again. Problem for our species is, of course, that what happens is that babies have to be born through those now narrowed hips. So babies have to be born through these now narrowed hips, and in the modern species what's that done is to leave a difficulty, and the difficulty of giving birth is something that all females will become aware of if they're not already aware of it. 20 to 28% of all births now are caesarean sections, so rather than babies being delivered through the birth canal where it's very tight and very squeezed because of the bone structure, what happens is that now we've taken a step that evolution couldn't take. What we've done through caesarean section is move the birth canal above the pubic bone. So the caesarean section effectively means that the baby can be born here instead of through this part here. So that's why then the caesarean sections are doing the job that evolution wasn't able to do. That was a too big a leap for it to do. Even in the modern species, without medical help, women get a lot of difficulties, particularly in parts of Africa known as the Fistula Belt, where about 1 in 7 women will die in childbirth because of the problems associated with it. What happens is that the baby is trying to be born, but the hips aren't narrow enough to allow that to happen. So if I can just show you the process. This is a small baby, it's not real, no babies are harmed in the making of this film. These are the hips. The journey that the baby has to make is such, okay? And you can see for yourself immediately how tight that is. This is a life-size model of a full-size human pelvis. It's obviously a small woman, but it's nonetheless, this is an adult pelvis. This is what the baby will be born through. When I first acquired this, I got another set of hips that I thought were life-size, but they turned not to be. They turned out to be 3/4 size only. But I can tell you that the difference between these crests just here, the biiliac crest, was only 1 centimetre. So 3/4 life size versus life size is 1 centimetre. It's not a big difference at all. As far as females are concerned, this is very, very important because the hips are slow growing compared to the rest of the body, and they don't reach their full adult size until women are about 25. So what this does is to give an indication of one of the paradoxes of the human species, which is that females are fertile in their early teens, but typically don't tend to give birth to their first child until they're in the mid-20s, because I think, and the thinking is, that the hips only then get to the full adult size, and only then is it really safe to do so. So very, very heavy toll of bipedalism. This slide shows you the source of the problem, and it's, as I've said, that as the species becomes bipedal, the hips become narrower because that's stable for locomotion. They need to stay just wide enough to give birth, and in humans, they're only just wide enough, literally only just wide enough. The ratio of the birth canal and the size of the baby to go through it, if you took it as one, would be just the head and the birth canal are the same size. Humans, the head is slightly larger than the gap available for it to go through. So this slide shows you that this is a problem that's been with us for a long time. It's a problem that the other primate groups don't share because they're not bipedal. This slide shows you that with that arrangement of the hips being narrow, the baby's path through those hips is not a straightforward one. In fact, what it has to do is to start sideways and then make a twist, because that's the only way that it can avoid all the nodules and the bony bits that it has to avoid. Unfortunately for our species, the baby takes the wrong turn. And if you look at the picture of the primate there giving birth, what you can see is that as the baby primate is being given birth, it comes out of the birth canal and its backbone is in a plane where what the mother can do is to help the baby out like that. So the baby just smoothly comes out. With our babies, because of the way they've turned, the backbone is in exactly the wrong plane. So the babies, if that's the mother's face up here, if the mother's stomach up here, this is the ground in it. Our babies are born the wrong way. If I can go back to the model again, they're born that way. Okay, so if the mother's birth canal is there, then that means that she can no longer help the baby out, because if she does that, then that's going to pull the back in the wrong direction, and that makes it very difficult. So immediately you can see that as a bipedal species, females of our species need to recruit the help of other females or their partners or their mates or whatever. So immediately you see that evolutionary step changes our behaviour dramatically.